Good morning, everyone. Let me review what we did last time. We discussed injective dimension of modules, and we gave a criterion. If you have a Noetherian local ring and M is a finitely generated R module, then the injective dimension is supremum of I, so that X I R Km is not equal to 0. The depth of a module is infimum of I, so that X I R Km is not equal to 0. And injective dimension has to be is the supremum of I, so that X I Km is not equal to 0. Then we proved a formula. In some sense, it is equivalent to the Oscillander-Buchsbaum formula. So suppose N is a finite R module, then the injective dimension of M is depth of N plus supremum of I, okay, so that X I and M is not equal to 0, where M and N are any finite R modules over R. Okay. And then we showed that the dimension of a module is bounded above by injective dimension. And if the injective dimension is finite, it is always equal to depth of R. Okay. As opposed to projective dimension, which can take any value between 0 and depth of R. But injective dimension only achieves the value depth of R. Okay. So all modules of finite injective dimension have same injective dimension, namely depth of R. So in this inequality 3, if you put M equal to R, then it will say dimension of R is bounded above by depth of R, but we know that depth of R is bounded above by dimension. And therefore, rings of finite injective dimension are Cohen-Macaulay. Okay. Cohen-Macaulay rings need not have finite injective dimension. It is a strictly smaller class in the class of Cohen-Macaulay rings. And Hyman-Bass defined Gorenstein rings to be rings of finite injective dimension. Okay. But we have defined, we took the classical definition of Gorenstein rings due to Northcott-Rees. And that definition was a ring is called Gorenstein if R is Cohen-Macaulay, and some ideal generated by system parameters is irreducible. So today's main theorem will prove that these two definitions are equivalent. That is, if a local ring has finite injective dimension, if and only if it is Cohen-Macaulay, and every ideal generated by system of parameters is irreducible. Okay, that is the main theorem I want to prove today. So it makes no difference whether you consider rings of finite injective dimension or rings which are Cohen-Macaulay having one irreducible system of parameters. Okay, so now we begin our new material, and one of the main techniques in the proof today is a theorem of Rees. This is called change of ring principle for Ext. So suppose R is a ring. R is a ring, and M and N are R modules. X is in the annihilator of N, and it is M regular and R regular. It is regular on both the module and the ring. R regular, and the element is in the annihilator of one of the modules, but on the other module and the ring, it is a regular element. Okay. Now consider an injective resolution of M, that epsilon be E0, E1, E2, etc., that this be, let this be an injective, a minimal injective resolution. A minimal injective resolution of M. Okay. Yeah. And now define EI prime to be HOM R mod XR EI. Okay. So you know that this is isomorphic to the annihilator of X in EI. Okay. And by one exercises which I assigned last time, this is a injective R mod XR module. Okay. All these are injective R mod XR modules. And so we get this sequence. We get this sequence. We will show that E0 prime is actually 0. Okay. So we get E1 prime and E2 prime, etc. Okay. Let us call these as E prime. Okay. These are all injective modules, but this is a minimal injective resolution of M mod XM. This is a minimal injective resolution of M mod XM. Okay, so we have to prove the exactness at E2 prime, E3 prime, etc. And the kernel of the first map between E1 prime and E2 prime is M mod XM. Okay. And then we have to prove the minimality. So that is the first conclusion, that from minimal injective resolution of M, if X is M regular and R regular, we can get injective resolution of M mod XM simply by taking HOM R mod XR to EI and dropping E0. Okay, drop E0. So this is a minimal injective resolution. And this implies two facts, that the injective dimension of M mod XM as R mod XR module, okay, is equal to injective dimension of M minus 1. So injective dimension goes down when if you take M mod XM over R mod XR. Third, that this is the change of ring principle, is called the change of ring principle. X I plus 1 R, okay, NM is isomorphic to X I R mod XR and M mod XM. So this X is in the annihilator of N. It is regular on R. It is regular on M. Then I plus first X is isomorphic to ith X of N, M mod XM, R mod XR. This is very useful to calculate the X, because if you have enough M regular and R regular sequence, many times you can reduce it to HOM. Okay. So these are the three conclusions. This sounds technical, but this is the heart of many arguments. So we'll keep on using this formula for injective dimension. If X is M regular and R regular, injective dimension of M mod XM over R mod XR is 1 less than injective dimension. And this follows from number 1. And number 1 actually implies number 3 about the X modules. Okay. This is very crucial. So let me give a sketch of a proof. It's a theorem in homological algebra, manipulating injective resolutions. So I will sketch a proof of this and show you applications. Any doubts on the statement of this theorem? Yeah. Any questions? Okay, so let us look at the proof. All right. So we are given this injective resolution of M, and using this, I want to get injective resolution of M mod Xm. Okay. And so look at HOM R mod XR E. Okay. This is a complex of injective module. This is a complex of injective modules. Remember, this is follows from this general principle that if I have a algebra homomorphism and suppose E is an injective R module, okay, E is an injective R module, then I can produce an injective module over S simply by taking HOM, okay, HOM S E over R. Okay, then this is an injective S module. So I'm applying this result to S equal to R mod XR. EIs were the injective modules over R, and HOM R mod XR, E are injective modules over R mod XR. Okay. So when I apply HOM, the given exact sequence gets converted into a complex of injective modules. I want to show that it is exact at most of the stops. It is a acyclic complex, and whose only non-vanishing homology is right in the beginning, and that is equal to M mod XR. Okay, so this will show that it is an injective resolution, and then I will show the minimality. Okay, so this is a complex of injective modules. Yeah, so we get E0 prime, E1 prime, and these maps are induced from maps of E1, EI to EI plus 1. Okay. When I apply HOM R mod XR, there are induced maps on these modules, on these injective modules. So I get this complex. Okay, I get this complex, and how to get the X modules of R mod XR M. Okay, to get X modules of R mod XR M, I can take injective resolution of M and then apply HOM R mod XR M and then take the homology. Okay, so this complex will give me the various X modules of R mod XR comma M. But they are, okay, we just apply HOM R mod XR, then we get these EI primes, and the X will be calculated as homology. Okay, now this E was given to be a minimal injective resolution. Okay, what is the meaning? E is minimal injective resolution, is a minimal injective resolution of M. Okay, that means if I look at the map En to En plus 1, okay, if I look at this map and then take the kernel of this map, this is a submodule. To say the E is a minimal injective resolution means this is an essential extension. Means En is the smallest injective module which contains the kernel of Dn. Okay, that's the meaning of minimal injective resolution. Okay, this you have learned in Prof. Gupta's lectures, how to construct a minimal injective resolution. Yeah, so that is the condition, that the kernel of Dn for every n is a essential extension of kernel of Dn. Yeah, but now you look at E0 spot, E0 to E1, and then the kernel of E0. What is the kernel of E0? E0 to E1. Can anybody tell me what is the kernel of E0 to E1?
M.
Yeah, kernel will be M, right? because it was an injective resolution. So this is an exact sequence. Okay, this is an exact sequence. That means E0 containing M is an essential extension. Yeah, it's an essential extension. And X is M regular. X is M regular. So do you see that X is also E0 regular? Can anybody tell me why X is E0 regular? What is the meaning of essential extension?
If kernel of the multiplication map from E0 to E0 by X, if this is non-zero, then it must intersect M at some non-zero point.
Right.
Which is contradicting that X is M regular.
Very good. So that proves essential extension means non-zero submodules of E0 will intersect in non-zero submodules of M. Yeah. So if there was an element in E0 which kills X, yeah, then the annihilator in E0 of X will intersect with non-zero submodule of M, but that will violate the fact that X is M regular. So X becomes regular on E0. I hope this is clear. Yeah, X is E0 regular. If X is E0 regular, what can you say about E0 prime? E0 prime in form R mod XR E0. Yeah, what is this? This is isomorphic to annihilator in E0 of X. But we just know that, we just found that this is 0. So E0 prime has become 0. So we have to drop that E0 prime. Yeah. So E0 prime is 0. So we consider the complex E1 prime, E2 prime, etc. And we want to show that this E prime is minimal injective resolution of M mod XM. Yeah. Okay. So now we suppose you want to calculate X tie R mod XR and then M. Suppose you want to calculate this. Either you can have injective resolution of M or you can have a projective resolution of R mod XR and then take the homology. Both are same. So X is R regular. So R mod XR has a free resolution. R mod XR has a very nice free resolution. Okay, this is a minimal free resolution of R mod XR. So I just apply hom dash M to this to calculate the X. Apply hom R dash M to star to calculate all these X. So what can you say about X tie beyond 1? Yeah, the length, this is R mod XR has projected dimension 1 over R. So therefore X tie R X tie R of R mod XR M, this is 0 for all I not equal to 1. Do you agree with that? Yeah, does everybody see
Yes.
this?
Yes, yes.
Because of the length of the resolution, x2, x3, they're all 0. And x0 is hom r mod xr m is that is 0 because x is m regular. So the only non-vanishing x is x1. Okay. So therefore, when you look at this complex E prime, in this E prime, it is exact starting from here. Because all the x's beyond 1, they are all 0. So we have to just look at the kernel of E1 prime to E2 prime. And that is equal to m mod xn. What is, how to find x1 of r mod xr m. How to find this? Well, we have this complex. We have this free resolution r to r mod xr and apply hom r dash m to get the complex. Okay, this is a covariant functor or contravariant functor? Hom r dash m, is it a covariant or contravariant?
Contravariant.
Contravariant. Yeah. So it will tell me hom r, okay, r mod xr is left exact to hom r m, and this is multiplication by x. So this is also multiplication by x, hom r m. Yeah. So, and then I get x1 r mod xr m, and then it becomes 0. Okay. But this is same as m. This is also same as m, right? So x1 is the co-kernel of the previous map, and therefore it is m mod xn. Yeah. So homology here at E1 prime turned out to be m mod xn. And all the other homologies are 0. So that says that this is an exact sequence. This is an exact sequence of injective R mod XR modules. Yeah. I hope this is clear to everyone. Yeah. So exercise. Show this in the tutorial. Show this is this hom, this E prime. E prime is minimal injective resolution. So you have to look at the essential property of the various kernels. Yeah, kernel from E1 prime to E2 prime should be essential submodule of E1 prime. Kernel of E2 prime to E3 prime should be essential submodule of E2 prime, etc., etc. This essential property will come from the essential property of the original injective resolution. And I'm leaving this an exercise for next tutorial. Show that E prime is a minimal injective resolution of M mod xn as an R mod XR module, because all these EI primes are injective R mod XR modules. Yeah, EI prime is hom R mod XR M. Okay, I mean EI, and this is injective R mod XR module by exercise that I assigned for today. Okay, and now you see that there is a shift. E0 prime has disappeared. Okay, E0 prime has disappeared. Okay, so if M had finite injective dimension, then this E had length equal to depth of R, and when I apply HOM R mod XR M, then I get injective resolution, finite injective resolution of M mod XM, but E0 prime has gone, and therefore the injective dimension reduces by 1. Is that clear? Yeah. Injective dimension of M mod XM over R mod XR is injective dimension of M minus 1. Because here E0 prime has disappeared. That turned out to be 0. So if M had a finite injective resolution, yeah, minimal injective resolution, we know that its depth has to be, its length has to be depth of R. And then I get this M mod XM injective resolution for M mod XM, but E0 prime has gone. Okay. And I have this minimal injective resolution, and therefore injective dimension of M mod XM will be 1 less than injective dimension of M. Yeah. And the same fact about the Ext, there is a shift. There is a shift in the Ext modules. So I plus first Ext of this conclusion that the I plus first Ext is change of ring principle. That I plus first Ext, I plus first Ext of R. I mean, we have to bring in another module. So NM I plus 1 is isomorphic to Ext I R XR M mod XR. Okay. So to calculate Xt plus 1 NM and to calculate the Xt of M mod XR, I have injective resolution of M. I apply HOM and dash and calculate the homology. Okay. Then to calculate the ith Ext of N M over XR, I need injective resolution of M mod XR, which I have produced here. Okay, and apply HOM and to this, use HOM tensor duality, and then you will see that these two are exactly the same. Okay, it's just little bit matching the indices, nothing more. Okay, so this also once I see that, once I have injective resolution of M mod XM, this fact is not difficult to prove. Okay. So prove, this is a tutorial. There are many proofs of this change of ring principle of Rees for Ext. Many proofs. Every book gives a different proof. But this is one of the simplest proofs that from a given in minimal injective resolution, I can produce a minimal injective resolution of M mod XM if X is M regular and R regular. Both conditions were required. And that implies the fact about injective dimension of M mod XM reducing by 1 and the Ext modules having this relation. Okay. Any doubts? Any doubts on this? All right, so let us now prove some very, very basic facts about Gorenstein rings. So now, from now onwards, we will show that rings of finite injective dimension are same as Cohen-Macaulay rings in which system of parameters produce irreducible ideals. Okay, but using the injective dimension definition, it is far easier to prove properties of Gorenstein rings because we have a homological tool. Yeah, we have a homological tool to test. Yeah. So the homological tool tells us how to prove injective dimension is finite, and then if I have injective resolution, I could get injective resolution of M mod XM, and this will give us properties, stability properties of Gorenstein rings. So here is the first result using this change of ring principle. So R is any Newtonian ring. Okay. And if R is Gorenstein, so Gorenstein ring is one, so that when you localize at any maximal ideal, I get a Gorenstein local ring. Yeah. So we have defined Gorenstein local rings. So non-local rings are called Gorenstein if the localization at any maximal ideal is a Gorenstein local ring. So if R is Gorenstein, then then S inverse R at any multiplicative set is Gorenstein for any multiplicatively closed subset S. So localization of a Gorenstein ring is Gorenstein. Yeah. Then suppose I take a regular element. Suppose X is R regular. Okay. Then R Gorenstein implies R mod XR is Gorenstein. And converse is true if R is local. This was the case with Cohen-Macaulay property also. Yeah, if R is Cohen-Macaulay ring, then R mod XR is Cohen-Macaulay if X is non-zero divisor. But to lift the Cohen-Macaulay property from R mod XR is not possible unless R is a local ring. Yeah, same fact is true for Gorenstein rings also. So converse is true. Converse is true if R is local. Otherwise, you can give an example, like we constructed an example of a ring where R mod XR was Cohen-Macaulay, but R was not a Cohen-Macaulay. Okay. Yeah. So let us prove this. So I'm given that R is Gorenstein. And S is a multiplicatively closed subset. I want to show that S inverse R is Gorenstein. Now, these are not local rings. So S inverse R is Gorenstein if and only by definition, if I localize this at maximal ideals look like S inverse P. Yeah, for some prime ideal of R. Yeah, the maximal ideals of S inverse R of the form S inverse P. So this is Gorenstein for all S inverse P which are in maximal ideal of S inverse R. Yeah, but S inverse R localized at S inverse P. Okay. This is isomorphic to R localized at P. Yeah, successively you localize, then I mean it's a transitive process. So this S inverse R localized at S inverse P is really RP. So I need to prove RP is Gorenstein. What is given is R is Gorenstein. So R localized at any maximal ideal is Gorenstein. But this prime ideal P is contained in some maximal ideal. So find this maximal ideal which contains P. Then R localized at P is same as R localized at M, PRM. Yeah. Okay. But RM is Gorenstein. That is given. Okay. RM is Gorenstein. So I have a Gorenstein ring. And when so it has finite injective dimension. So when I localize, I get an injective resolution of localization. So R has finite injective dimension. So there is a finite injective resolution of R, and when I localize, this remains the exact sequence this remains exact sequence. Okay, so RM was Gorenstein. So when I localize at PRM, I get this injective resolution, because localization of injective module is injective module. Yeah, if M is R injective, then S inverse M is S inverse R injective module. It's a small exercise for you to prove. Okay, so localization of Gorenstein ring is Gorenstein. Just try to prove this using the classical definition, and you will get stuck. This is analogous to what went on in a regular local ring, that we got a homological characterization of regular local ring, and using the homological characterization, it was easy to prove that localization of a regular local ring is regular local. Same thing is happening here. Yeah? If you use the classical definition, it is not clear how to prove that a localization of Gorenstein ring is Gorenstein. But once you have this homological characterization that these are exactly the rings of finite injective dimension, then it is easy to show that localization of rings of finite injective dimension we again have finite injective dimension. Yeah? So therefore it is Gorenstein. So Gorenstein property is a local property. Okay. Let's look at part 2. This is called specialization. So if X is R regular, X is R regular, and R Gorenstein, then I want to show R mod XR is also Gorenstein. R mod XR is also Gorenstein. Yeah. So to prove that R mod XR is Gorenstein, I must prove that localization at every maximal ideal is Gorenstein. Okay. Maximal ideals of R mod XR look like M mod XR. So this I must prove that RM over XRM is Gorenstein for all maximal ideals. All maximal ideals M containing X. Okay. But I know R is Gorenstein, so RM is Gorenstein. And this is going mod a non-zero divisor. X is non-zero divisor in R, it is a non-zero divisor in RM also. Okay. So X is a non-zero divisor in RM, RM is Gorenstein. Okay. So it has finite injective dimension, right? But I know injective dimension by change of ring principle, injective dimension of R mod XR, if you have a local ring, yeah, this is equal to injective dimension of R minus 1. So this RM has finite injective dimension, and when I go mod X, yeah, then this formula says that RM over XRM also has finite injective dimension. It is exactly one less. Therefore, it is Gorenstein. Is this clear? Yeah. So it implies R mod XR is Gorenstein. Again, this property is not easy to prove using the classical definition. We assumed that if you take quotient of a regular local ring, then it was Gorenstein. But now we have proved a generalized version. R is Gorenstein, then R mod XR is also Gorenstein if X is a non-zero divisor. For the converse, this argument shows that I can assume that the ring is local. Okay. Converse, R mod XR, Gorenstein. I want to show R is Gorenstein. Okay. So we have to localize at maximal ideals. Take a maximal ideal of R, and we want to localize and prove that it is Gorenstein ring. But you see, R mod XR, when I localize at M, it is RM over XRM. Okay. So I want to show RM is Gorenstein. But what I know is RM over XRM is Gorenstein. So I know injective dimension of R mod XRM is finite. But this formula of injective dimension says that injective dimension of RM is also finite. Right? So injective dimension of RM is also finite. Yeah. So converse is also true by using the formula for injective dimension. Another corollary, a regular local ring is Gorenstein. Regular local ring is Gorenstein. Yeah. So suppose this is D-dimensional regular local ring, D-dimensional regular local ring. So maximal ideal is generated by D elements. And we know that regular local ring is a Cohen-Macaulay ring. So any system parameters is a regular sequence. So X1 up to XD is a regular sequence. It's a regular sequence. This is a regular sequence. Right? It's a regular sequence. And to show that it's Gorenstein, I must prove that it has finite injective dimension. But injective dimension of R is equal to supremum of I, so that XI R K R is not equal to 0. So I have to examine the XI of KR. But R is a regular local ring. So K has a minimal free resolution. K has a minimal. To calculate this X, I can take the minimal free resolution of K and apply Hom dash R and calculate the cohomology. So K has minimal free resolution given by Koszul complex. Okay, this is the Koszul complex R to RD, RD choose 2, R to K to 0. Yeah. So you have minimal free resolution given by Koszul complex of R mod M, and then just apply Hom dash R and calculate the homology. Yeah. But we know that this ring is Cohen-Macaulay. Regular local ring is Cohen-Macaulay. So all the XI of KR, they are 0 for I less than D. Because M contains a regular sequence of length D. So all the XI less than D, they are 0. But higher XIs are also 0 because of the length of the resolution is D. Okay, by the length of the resolution. Maybe I should not write on this. Yeah. So the Koszul complex tells me that XI R K R is 0 for all I bigger than D. Okay, and XI R K R is 0 for all I less than D, because this is by Cohen-Macaulay property, and this is from the length of resolution. So there's only one non-vanishing X. Yeah. Can somebody tell me what is this? What is this? Yeah, now I have a new tool to calculate X. This is XD minus 1 R mod X1 R, okay, K R mod X1R. Keep doing this until you get Hom R mod MR K R mod MO. Okay. But this is Hom KK and this is isomorphic to K. So therefore, XD R KR is equal to K. It turned out to be K. We will show that this is always true. If a local ring has finite injective dimension, d text of KR is the only non-vanishing hext, and it will turn out to be K. This is what has happened for regular local ring. Yeah, for regular local ring, XD KR is K. Okay, so this proves that regular local ring is Gorenstein. I have proved that the injective dimension of R is D. Any questions on this?
Sir?
Yeah.
Sir, when I don't understand why we need, for the converse part, why
Yeah.
do we need R to be local? Can you please explain once again?
No, say that again.
For the converse part of 2,
Yeah.
We need R to be local for showing R is Gorenstein.
Right.
So why do we need that local condition?
Yeah. So it is similar to the Cohen-Macaulay situation. You remember in Cohen-Macaulay case, R mod XR could be Cohen-Macaulay without R being Cohen-Macaulay.
Yes. Yes.
Yeah.
Yeah.
So that's what goes wrong there.
Okay.
Yeah. So the proof. Let me go back. The proof says that RM over XRM is Gorenstein. Yeah. So if R is local, then I'm giving that R mod XR is Gorenstein. Okay.
Yes.
But then when R is local, the injective dimension of R mod XR and is equal to injective dimension of R minus 1. I mean that property is true without R being local. Sorry. Yeah.
Okay. Yes.
Yeah. So it tells me injective dimension of RM is finite.
Means RM means R is same as RM here when I am taking R to be local.
Right. And X is a non-zero divisor in RM.
Yes.
And RM over X is given to be Gorenstein. So injective dimension of RM, I mean, let's call RM as R. R is local. So injective dimension of R mod XR over R mod XR is D minus 1.
Yeah, but I am saying that this formula is true for non-local rings also.
Yeah.
So,
but I want to show R is Gorenstein, I must localize and show that RM is Gorenstein.
yes.
So I need to prove the local property. So but X is given to be R regular, so it will become R regular as soon as X is contained in M. It will become RM regular. Okay, so take all those maximal ideals which contain X. Okay, and then RM over XRM is given to be because R mod XR is Gorenstein. Okay, so RM, this means by definition of Gorenstein that when I localize at maximal ideal, it is Gorenstein.
Yeah.
So R mod XR is given to be Gorenstein. So RM over XRM is Gorenstein for every maximal ideal. Okay. So now and I want to show that RM is Gorenstein. So everything is local now.
Yes.
We are reduced to local case.
Yes.
Okay. And you can modify that example that I gave where Cohen-Macaulay property did not lift. Okay. In that you can take a Gorenstein ring and non-Gorenstein ring.
Okay.
and take the direct sum, you will get a counterexample to this converse statement.
Okay, sir. I will check.
Okay. Yeah, maybe I'll assign that as an exercise to produce a counterexample to the converse statement. All right. Any other doubt? So what we observed here is that in a regular local ring, there is only one non-vanishing X, and that is at the dimension. Yeah, if dimension of a regular local ring is D, then dth X of KR turned out to be K. Okay. I want to show that this is in general true for rings of finite injective dimension. If the injective dimension is D, we know that D, the ring is Cohen-Macaulay, D is the dimension of R, then XD-KR, okay, we know it is non-zero, but actually it is one-dimensional. Okay, so in the class of Cohen-Macaulay rings, if you look at XD-KR, this is a measure of complexity of the local ring. Yeah, so it's we know it is non-zero. Okay, so the simplest one is simplest ring should be those where this is one-dimensional. XD-KR is one-dimensional, and that happens exactly when the rings are Gorenstein. Okay, so that's why Gorenstein rings have better properties, very interesting properties, as opposed to general Cohen-Macaulay rings. Right. Now let us prove the equivalence of the two definitions. Okay, we have Bass's definition, rings of finite injective dimension are Gorenstein. We have Northcott-Rees definition, Cohen-Macaulay rings in which one system parameters is irreducible. Okay, we want to show that these two classes of rings are identical. Okay, so theorem. Let Rm be local ring of dimension D. When I say local, I always mean Noetherian. Then the following are equivalent. One, injective dimension of R is finite. Second, injective dimension of R is dimension of R. Third, XI R KR is equal to 0 if I is not equal to D, and it is K if I equal to D. This we proved for regular local ring just now. Fourth, R is Cohen-Macaulay, and every system of parameters generates an irreducible ideal. 5, R is Cohen-Macaulay, and some system of parameters generates an irreducible ideal. Yeah. So if you have a Cohen-Macaulay ring in which one system of parameters is irreducible, then every other system of parameters is also irreducible. And this can be tested simply by computing the X, that the only non-vanishing X is at the dimension level and it is equal to K. Okay. And these are rings which have finite injective dimension. These are the my numbering is wrong. This should be, yeah, no, it's correct. Right. Okay, so this establishes the equivalence of the classical definition and the homological definition. Right. So let us prove 1 implying 2, we have already proved. Injective dimension of R is finite, then we know it is a Cohen-Macaulay ring. Yeah, we have already proved that this implies R is Cohen-Macaulay, and the injective dimension therefore is depth of R, which is dimension of R. Okay, so this we have already done. Number 2, okay, injective dimension is D, then I want to calculate the X. Yeah, 2 implies 3, right? So if the injective dimension is D, equal to depth of R. Injective dimension is always depth of R, okay, equal to D. Then of course R is Cohen-Macaulay. Okay, R is Cohen-Macaulay, and so this says that the X tie R KR is 0 for I less than D, because this is a Cohen-Macaulay ring, and because injective dimension is also D, X tie R KR is 0 for all I bigger than D. So we only need to worry about D text. So what is the D text? Yeah, what is the D text? Okay, we need to show that D text is isomorphic to the residue field. So to prove this, apply induction on the dimension. Induction on D. So let D be equal to 0. Then I have R10 local ring. Rm is R10 local ring. And assumption is that it has injective dimension, finite injective dimension, that is dimension of R. So injective dimension of R is 0, because it is equal to dimension of R. Okay, and it is equal to depth of R. Depth of R is 0. So injective dimension is 0. So that says that R is an injective module. R is an injective R module. Is this clear to everyone? Any doubts? I want to show that D text of KR is isomorphic to K. I'm applying induction on the dimension. When dimension is 0, it's an R10 local ring of finite injective dimension, but we know its injective dimension has to be depth of R. Depth of R is 0, so injective dimension is 0. So therefore, R is an injective R module. Yeah, R is an injective R module, but depth of R is 0, implies maximal ideal is an associated prime, and that says K injects into R, and I can take the co-kernel. So this is an exact sequence of R modules. R is injective R module. So what can you say about Hom dash R? What can you say about Hom dash R? Somebody should tell me what kind of functor is this? Shrikant Shekhar?
Contravariant.
And what else?
Exact functor.
It's an exact functor. R is injective R module.
Yes.
So this is contravariant contravariant exact functor. Okay. So when I apply on this exact sequence, that gets reversed. So I get hom r r mod k r hom r r to hom r k r, and then I get 0. Okay. Yeah. Now R is Artinian ring, so it has finite length. So R mod k has finite length. Suppose length of R is say L. What is the length of R mod k? What is the length of R mod k? L minus 1. No? This exact sequence says length of R is length of k plus length of R mod k. So this has length L minus 1. Yeah. And hom RR is what? This is isomorphic to R. Okay. And hom KR is equal to X0 R KR. Right? Can hom KR be 0? Is hom KR non-zero or 0?
Non-zero.
This is non-zero because K injects into R. There is an injective morphism K to R. This is a non-zero module. It is a homomorphic image of R. Okay. So what can you say? What can you say about its number of generators? This is cyclic, no? It's a quotient of R. It's a vector space. So it is one-dimensional vector space. So hom R KR must be isomorphic to K. Hom KR is killed by M. It's a R mod M vector space. Okay. But it is homomorphic image of R. So it is cyclic and it is non-zero. And therefore it is isomorphic to K. Is this clear? Any doubts on this? So have we proved the theorem for D equal to 0? Pradyumna, is it clear that we have proved the theorem for D? I mean, 2 implies 3 for D equal to 0.
Yes.
Yeah, we had to prove that the highest non-vanishing X is isomorphic to K, and here D is 0, so highest non-vanishing X is just hom. And we have proved it is isomorphic to K by observing that R is an injective R module. The injective dimension was 0, so R is injective R module, and that allowed us to prove this fact about the only non-vanishing X is isomorphic to K. Okay, so now we can proceed to higher dimension. So let dimension of R, let D be bigger than or equal to 1. Okay, what am I supposed to prove? I'm supposed to prove that D text of KR is isomorphic to K. Yeah, but now you see when D is at least 1, there exists, the ring is Cohen-Macaulay, ring is Cohen-Macaulay, so there exists an X in M which is a non-zero divisor on R. Yeah, this is a non-zero divisor on R. So how do you calculate D text? By Ries's theorem, this is isomorphic to this. Yeah. So how to complete the argument? R has finite injective dimension, then R mod XR has finite injective dimension. This we have proved. So by induction hypothesis, this is isomorphic to K. By change of ring principle of Rees, D X is also isomorphic to K. Yeah. What about the other X? Well, X I plus D R K R is isomorphic to X I plus D minus 1 R mod XR K R mod XR. Okay. So all the X beyond D, they are 0. So this says that these are 0. This says that these are 0 for all I bigger than or equal to 1. And for less than D, they are anyway 0 because R is Cohen-Macaulay. Beyond D, they are 0 because of this induction hypothesis. And D text is isomorphic to K because D minus first text of R mod, K comma R mod XR is isomorphic to K by induction. Okay, so this change of ring principle of Rees is very useful because it brings down to proving the theorem for dimension D to Artin local rings. Any questions? Any questions on this? Okay, so let us go to the next implication, namely 3 implies 4. Okay, so I have my assumption is that I have this local ring where the only non-vanishing X is this one, and this is isomorphic to K. Okay, and all the other X are 0. For all I not equal to B. Okay. And I want to show that this implies R is Cohen-Macaulay and any system of parameters generates an irreducible ideal. Okay. Now the first condition, X I KR is 0 for I not equal to D, tells me that the depth of R is D. Depth of R is equal to min of I, so that X I R K R is not equal to 0, and we know in this case it is equal to D, and therefore R is Cohen-Macaulay. That is the Cohen-Macaulay property. Now we want to show that any parameter ideal, that is any ideal generated by system parameters, is an irreducible ideal. And we know how to do that. To test whether any parameter ideal is irreducible, I have to go mod that ideal, get an Artin local ring, and calculate its socle. And what should we prove about the socle after you go mod a system of parameters? To prove that it is irreducible, what do we have to prove about the socle?
It should be one dimensional.
One dimension. Yeah. So if X bar is an SOP, then D text, I know D text of KR is isomorphic to K, yeah, but by change of ring principles, this is equal to Hom R mod XR K R mod XR. but this is equal to x colon m over x, which is socle of R mod x. So socle of R mod xr is isomorphic to K. So it is one dimensional. And therefore, X bar generates a irreducible ideal. Is this clear? If among all the non-vanishing x, Kr, if dth x is the only non-vanishing x and it is equal to K, then this implies that the ring is Cohen-Macaulay and every system of parameters is irreducible. Any doubts on this? Okay, now we prove the converse, the remaining part, that is 5 implying 2. And 4 implying 5 is clear. Okay, it is 5 implying 2. I'll prove 5 implying 2. 1 and 2 are equivalent. Yeah, so it's enough to prove that 5 implies 2. So 5 says R is Cohen-Macaulay and it has a system of parameters x bar such that x bar R is irreducible. This is exactly Gorenstein rings in the sense of North Cotton rings. And 2 says that injective dimension is D. So we are going to prove that this implies that injective dimension of R is D. Okay, that will finish. But you see, to calculate the injective dimension, I have to show that there is, and to show it is D, I have to show that the only non-vanishing X happens at Dth level. Okay, but now the ring is Cohen-Macaulay. So below D, all the X type Kr are 0. R Cohen-Macaulay means below D, these are 0. Yeah. I have to show above D also they are 0. Okay. But X D plus I Kr is isomorphic to X I R mod. Suppose this system of parameters generates a M primary ideal Q, then by change of ring principle, X D plus I Kr is same as X R mod Q I K R mod Q. The ring is Cohen-Macaulay, X1 up to XD, we generate Q, that is a regular sequence. So by change of ring principle, XD plus I is X type K R mod Q, R mod Q. But R mod Q is Artinian local ring. And the zero ideal in R mod Q is irreducible. Because Q is irreducible by assumption. So zero ideal of R mod Q is irreducible. So I have a Artin local ring whose zero ideal is irreducible. And because of this change of ring principle, I can just prove the theorem for Artin local rings. And therefore, 5 implies 2. 5 implies 2 can be proved for Artin local rings. To get it for arbitrary Cohen-Macaulay rings. because I will show for I equal to 0, I will show that x of R mod Q, I mean Hom of R mod Q, K R mod Q is K, and that will say that dth x of KR is K. And other x's are 0. I will show that for R mod Q, x1, x2, etc., they are all equal to 0. So this will say that xi of KR is 0 for I bigger than D. Yeah. So we have brought down by change of ring principle in all these proofs. We invoke the change of ring principle for X and reduce the general problem to a same problem for Artin local rings. Is this reduction clear to everyone? How the general proof of 5 implying 2 in dimension D has been reduced to proving the same implication for Artin local rings. Any doubts? Omkar Javadekar, are you with me, Omkar?
Yes, sir, it's clear.
Yeah. So what do we have to prove about Artin local rings now?
Yeah, we have to prove that Hom KR is non-zero and higher X are 0.
Yeah, and Hom KR
Is isomorphic to K.
right. Okay, good. So we now let R be Artin local. Okay, R be Artin local, and where zero ideal is irreducible. Okay, and then I want to show that Hom R KR is isomorphic to K, and X tie KR is 0 for all I greater than equal to 1. Yeah, but Hom KR is really the socle, and so therefore the socle of the zero ideal. So socle of R is one-dimensional. This says that the socle of R is one-dimensional because zero ideal is irreducible. By assumption, zero ideal is irreducible. So socle R is one-dimensional. So therefore, this is isomorphic to K. Now we show that higher X star 0. It remains to prove that X tie R KR is 0 for all I bigger than equal to 1. Okay. Now R has finite length. R is Artin. R is Artin local. So suppose length of R is R. Then there exists a sequence of ideals. Okay. Sequence of ideals. 0 equal to I1 contained in I2 contained in IR equal to R. Okay, such that I plus 1 over I is isomorphic to K. Yeah. This is from the general principle that you can finite module over a Newtonian ring can be filtered by submodules so that the quotient modules in that filtration are isomorphic to R mod some prime ideal. But there is only one prime ideal here. So namely maximal ideal. So all the quotients have to be K. The length is R, so I have a Jordan-Holder series of length R. And the Jordan-Holder series consists of ideals of R. So I'm taking this Jordan-Holder series of R so that the quotients are isomorphic to K. Okay. I want to show that X tie KR are 0. Okay. X tie KR is 0 for I bigger than equal to 1. And so I will split this entire Jordan-Holder series into a sequence of short exact sequences and get my conclusion. This is general trick for proving many theorems. Yeah. So because of this filtration, we have the following exact sequences. Zero to I1 to I2, and the quotient is K. 0 to I2 to I3, and the quotient is K. Okay. Finally, 0 to IR minus 1, IR is R to K to 0. So I have these short exact sequences. Yeah. So apply harm R dash R to these, because I want to calculate x tie of KR. Okay, I want to calculate x tie of KR. K is hidden in each one of these short exact sequences. To get x tie KR, I can just apply harm dash R and hope to calculate the x ties. Okay, so when you do that, take it on the rth one. Rth one is IR. Okay, so yeah, so when you do that, let us look at the first sequence. Let's look at the first sequence. So this is a contravariant functor, and so I get this is left exact. So harm R KR to harm R I1 R to harm R I2 R harm R I2 R, okay. And then
I2 first, then I1.
I2 and I1. Yeah.
Yes.
Yeah. And then what comes here?
X1.
Next, 1 R
Here.
K. And then
I2, X1 is I2.
yeah. So this is this map is a connecting homomorphism. Let us call this as delta 1. In the long exact sequence, the first connecting homomorphism is here, delta 1. Okay. Now, harm KR, what is that? By assumption, harm KR is K. This is K. Okay. This is K. Yeah. So I want to claim that length of harm R I R, okay, is less equal to I, okay, and equality holds if and only if delta 1, delta 2, delta I, they are all 0. These connecting homomorphisms are all 0. Now let us see whether this is true for I equal to 1. So if I take I equal to 1, I'll apply induction to prove this. So suppose I equal to 1. Yeah. If I equal to 1, what does it say? That the length of this harm R I1 R is less equal to 1, right? It is less equal to 1, and it is 1 if delta 1 is 0. So how do we see that? No, there is I equal to 1 is not that sequence. I equal to 1 is trivial. I equal to 1 case is trivial. Just a minute. Yeah. Take I equal to 2. That is the first non-trivial case. So when I equal to 2, then look at this part of the exact sequence. Okay. Look at this part of the exact sequence. This hom R I2 R. Okay. Now all these have finite length because R is K, they are into R is Artinian ring. It is killed by some power of maximal ideal. So hom is also killed by all the x's are also killed by some power of maximal ideal. So all the x have finite length. But if suppose this delta 1 is 0 map, if delta 1 is 0 map, then I get this short exact sequence hom R KR to hom R I2 R to hom R I1 R. If delta 1 is 0, I have this exact sequence. Okay. So this length is sum of these lengths. This length is 1. What about length of R I1 comma R? Okay. So 0 is I0, and this is contained in I1. And I1 mod I0 is K. So I1 is actually isomorphic to K. So this is also K. Okay. This is also K. So if delta 1 is 0, it says that length of hom R I2 R is 2 if delta 1 is 0. And converse is also true. If this length is is 2, then this I know that this length is length of this hom KR plus a length of a submodule of hom IR, because delta 1 may not be 0. Yeah. But if this length is 2, then it has to be a surjective map. By rank nullity theorem, it has to be a surjective map, and so delta 1 has to be a 0 map. Okay. So I have shown you this statement for I equal to 1 and 2. Yeah. And by induction, it is true for now. Look at the last one. Look at the last one. Last one says the length of hom R IR R. Okay. But IR is R. This is equal to R. So this length turned out to be R, and so by induction hypothesis, all the connecting homomorphisms have to be equal to 0. Okay, so this is equal to length of R, and so now you look at this sequence 0 to IR minus 1 to R to K. Okay, and apply hom dash R, and you will see that X1 R KR has to be length 1. This is isomorphic to K. Because I have the previous ones, all the delta i's are 0 below R minus 1 by induction. And then you look at the rth level and apply hom dash R, take a long exact sequence involving next, and you can, I'm running out of time, so you can read this rest of the proof. This is not difficult. Yeah. So I have proved part 2, which said that you prove part 2 for Artin local rings. By change of ring principle, we reduced to Artin local rings. And for Artin local rings, we had to prove that all the higher x are equal to 0. And x1, I mean, hom KR is isomorphic to K. That came just from observing that the 0 ideal is irreducible, therefore Sockle dimension is 1, and therefore hom KR is isomorphic to K. Okay. So this short exact sequences are helping us to prove that the higher X are all zero. Okay. Yeah, so we will stop here.